Welcome. In this video, we are going to talk through the answers to this page of net ionic equation mixed practice problems. And the thing to keep in mind when you're writing net ionic equation is that there are two types of things which will dissociate into ions when you place them into water. And what we call these things, if they dissociate into ions when you put them in water, we have a name for them. They're called strong electrolytes, FYI, little vocab term there. And strong electrolytes, there's two types of them. There's aqueous ionic compounds and aqueous strong acids. So we're trying to figure out what the net ionic equation is. I'm going to keep in mind that these two types of things will ionize. And then that's it. If it's not one of these two things, then it's not going to ionize. All right, so if it's a solid, not going to ionize. If it's like, liquid water, CO2 gas, not going to ionize. So it's only these two types of things. And the other thing we're going to practice is identifying the different types of reactions. So there's some notes here on page 6, and I have posted them off to the side here so I can refer to them easily. There's different types of reactions. We're going to practice identifying which is which. So this first one we're going to look at is a double displacement reaction. It's a precipitation reaction. So this is one that we've done some practice with already. And so we've got zinc nitrate and lithium carbonate. Notice that the formulas here are already given. And then in this type of reaction, the pattern is, we've got two aqueous compounds, is that the metals are going to swap places with each other, which means the lithium is going to go with the nitrates and the zinc is going to go with the carbonate. So notice the first thing I'm going to do is I'm going to write down the symbols and figure out who's paired with who. Then to figure out what the subscript should be, I'm going to look at the charges. And to look at the charges, I'm going to look at one of my reference pages that has all the ion charges on it. So I will see that lithium, because of where it is on the periodic table, I know lithium will form a +1 ion. And then nitrate is one of these polyatomic ions we should know, be familiar with. It's got a charge of -1. Okay, so there we go. And the rule is we want these charges to add up to 0. So these ones add up to 0. So perfect. I'm done. Let's look at these ones. Zinc carbonate. Zinc, if I look at my periodic table, has a charge of +2. That's zinc right here. Carbonate is a polyatomic ion. It's got a charge of -2. So you want to be referring to these tables until at some point, once you get enough practice, you'll be familiar enough where you just know them and you won't have to look up these numbers anymore. All right, so this is +2, this is -2. Cool, so I don't need subscripts there either. And then I want to label states of matter. So my solubility rules tell me anything with a nitrate in it or an alkali metal is going to be soluble. So you know this one's going to be soluble. And then my zinc carbonate is not on my list of soluble things, so it's going to be insoluble. And my solubility rules, they are listed in several different places, but one place where you could find them is right here on your reaction type summary page, and this was on page 6 in OneNote. So notice how nitrate compounds are always soluble. There you go. But notice how zinc and carbonate are not on my list of soluble things. So if it's not soluble, then it's going to be insoluble, so it'll be a solid. And then to find the net ionic equation, well, first let me balance it. I need 2 right here to balance it. Okay, to find the net ionic equation, I'm going to write out what we call the complete ionic equation first. So I'm going to keep in mind that anything if it's aqueous and ionic or aqueous and strong acid, it's going to split into ions. So that means that this one, since it's aqueous and it's an ionic compound, it's going to split apart into its composite ions. That's what it does when it's in water. That's what ionic compounds do. They split apart into ions when they dissolve in water. So all my aqueous ones are going to ionize. And then my one that's a solid, it's a solid. So it didn't dissolve, so it's not going to split apart in ions. So that one's going to stay put. And then we'll look for spectators. Boom, boom, boom. Lithium and nitrate, they're exactly the same on the left and the right. They're actually not really even involved in the reaction. So my net ionic equation is just going to show who's involved in the reaction. And that's zinc ions and carbonate ions combining to form this zinc carbonate precipitate. All right, now let's look at the second one. Solid magnesium and aqueous hydrochloric acid combine to form aqueous magnesium chloride. So this is an ionic compound, so I have to consider the ion charges. So magnesium is +2, chloride's -1. So I'm going to do a little crisscross and say, okay, I need 2 chlorines for every 1 magnesium, and it's aqueous, because we see it right there. And then hydrogen gas. So whenever you're writing down the formula for an element, like either magnesium or hydrogen, what you want to keep in mind is Hofbrinkel. Hofbrinkel tells us the diatomic elements. So hydrogen is part of Hofbrinkel, so it's H2. Magnesium, not part of Hofbrinkel, so it's just Mg. Okay, and now I want to balance it. There we go. So that is my molecular equation. And then let's write out, I'll use a different color pen here, the complete ionic equation. So what I'm going to do, I'm going to ionize anything that's aqueous ionic or aqueous acid. Okay, so magnesium, it's not ionic, it's not an acid, so it's not going to ionize. So it just stays put. But HCl, it is when it's aqueous, and it's one of these acids we talked about. So that means it will split apart into ions. So H+ ions and Cl- ions. Magnesium chloride, it's ionic and it's aqueous. So it also is going to split apart into ions. And then hydrogen gas, it is not aqueous. It's not ionic. So it's not going to ionize. So again, we only ionize aqueous ionic compounds and aqueous acids. All right. Once we do that, then we look to see if there's any ions that like don't change. And notice how in this case, we have one set of ions, the chloride ions, that don't change at all. So those are our spectator ions. So what's left over is solid magnesium, and then aqueous hydrogen ions. I'll label the states of matter on these ones. And then that turns into aqueous magnesium ions and then hydrogen gas. Okay. And then we'll see later on, this is something called a redox reaction. We'll talk more later about what that means to be oxidized and reduced. All right, here's another one. This one, the equation's already written out for us. This is potassium bicarbonate reacting with hydrobromic acid. So we just need to figure out what the net ionic equation is. So I'm gonna use my 2 rules here. I'm gonna ionize anything that's an aqueous ionic compound or an aqueous strong acid. So why don't I go through maybe and underline them first? So here's an aqueous ionic compound. Here's an aqueous acid. And then here's another aqueous ionic compound. Notice the water and the CO2, those are not aqueous, they're not ionic. I'm not going to ionize those ones. So I'm only going to ionize the ones that I underlined. Okay, so there's a strategy maybe you'll find helpful. So I'm going to split this into the ions. This is potassium and the bicarbonate ion. If you're not familiar with that yet, it's on our list. Let's scroll in here. Of the common ions to know. Bicarbonate, it's HCO3 with a -1 charge. Okay, that's one of the ones we want to be familiar with. And then HBr, it is aqueous acid, so it will also split into ions. Water and CO2, those aren't going to ionize. They just stay put. But then my potassium bromide, it will split into ions. And now when I say, do I have any spectators? Well, looks like potassium doesn't change at all, and then bromide doesn't change at all. So those are what we call spectator ions. So my net ionic equation would be this would be HCO3. So the bicarbonate ions are reacting with the hydrogen ions and forming liquid water and CO2 gas. And these are both dissolved in water. So the only time you'll get ions is when something's dissolved in water. Okay. So let's try this one. We'll go back to the black for the molecular version. All right. So solid iron. So notice how iron is not part of Hofbrinkel. So I'm just going to write it Fe. Okay, it doesn't get a sub. Only Hofbrinkel ones get a subscript there. So this is just Fe, iron. And then copper 2 nitrate. That means the 2 means the copper has a charge of 2. And then nitrate, if we look at our list of ions, again, these polyatomics, nitrate has a charge of -1. Okay, so I'm going to do a little, crisscross action here. So this is what the formula is going to look like. Let's see if I can go back and erase these. Okay, after I made a mess. I'll just rewrite that. Okay, NO3, 2, and then this is, oh, you know what? I left out states of matter here. This should say aqueous. This should say aqueous for the both of these solutions. That's my bad. I left that out of there. Okay, they're going to form solid copper. So since copper is not part of Hofbrinkel, we don't get any subscripts. It's just Cu. And then iron 3 nitrate. That means iron with a charge of 3. And remember, nitrate has a charge of -1. So it looks like I'm going to need 3 nitrates for every 1 iron. All right. And there we go. So I need to balance this. I've got 3 nitrates here, 2 nitrates here. Lowest common multiple of that is 6. So I'm going to put a 3 here. And then put a 2 here and a 2 here, and now I should be balanced. Got 6 nitrates, 6 nitrates. Cool. So that's my molecular equation. Now let's go through and do the complete ionic. And remember, our rule is we're only going to ionize aqueous ionic compounds or aqueous acids. All right. So my only aqueous compounds are these ones right here, and they're both ionic. So I'm going to ionize these 2, but nothing else. All right, so that means I'm going to have 2 solid irons, and then 3 copper plus 2 ions, and then 6 nitrate ions. And then I've got 3 solid coppers over here, and 2 iron ions, and 6 nitrate ions. All right, and then I'm going to look for any spectators. So the only one who's a spectator is this one right here, 6 nitrates. That's my spectator. So my net ionic is I've got 2 solid irons with 3 copper ions, and then 3 solid copper plus 2 iron ions. And if you're wondering what's the difference here, you might say, well, this is copper and copper. Isn't that just, doesn't look like anything's changing? Well, the copper, the aqueous copper ion is very different from like solid copper. So solid copper, think of like a penny, right? Versus the aqueous copper ion is like a blue liquid. So these are definitely 2 very different things, right? So aqueous ion is much different from like the neutral solid. So they're definitely, it's definitely going through a change there. Oops. So, okay. So now let's look at the next one here. This is another precipitation reaction. And as we're going through these, you know, feel free to skip ahead to the ones you need to, you know, need me to talk through slowly versus ones you think you can go through quickly. What's going to happen here, it's a double displacement. So the nickel and the sodium are going to switch places. So the nickel goes with the phosphate and the sodium goes with the nitrates. The way we figure out the subscripts is we look at the charges. So nickel, you see that says nickel 2 nitrate? That means our nickel has a charge of 2 in this compound. And then phosphate, if you look down at your list of polyatomic ions, phosphate is one of the ones you want to know. It's got a -3 charge. All right, so phosphate's got a -3 charge. So if you do a little crisscross here, this formula would be Ni3PO4 2. Okay, so that's the formula for nickel phosphate. Okay, there we go. And then sodium nitrate, sodium's +1, nitrate's -1. So we don't need any subscripts at all there. All right, now I want to balance it. Let's see. I've got 2, let's look at maybe balancing the nickels first. 3 nickels, let's put a 3 over here. That gives me 3 times 2, 6 nitrates. So I'm going to put a 6 over here to give me 6 nitrates. And then I'll put a 2 right here. And then now I'm all set. Now I've got a balanced molecular equation. All right, so now let's look at your states of matter. So any nitrate compounds are always aqueous. So it looks like this must be our precipitate. That's our solid. And then when we ionize things here, go back to my color coding here. I'm going to ionize any aqueous ionic compounds. So these 3 are going to ionize. My solid will not ionize. So that means I'm going to have 3 nickel plus 2 ions, 6 nitrate ions, 6 sodium ions. 2 times 3, got 6 ions there. And then 2 phosphate ions over here. And it is important that we write 6 sodium and not 2 Na3. That would be incorrect. The reason why we don't want to use a subscript is because if we write Na3, that makes it sound like they're all bonded together. So the subscripts implies that they're like bonded, which they're not. They're just 6 separate sodium ions. So it's important it should just say 6Na. And then over here, this one does not ionize because it's a solid, but then your 6 sodium nitrates will ionize. So we check for spectators. Boom, we've got 2 spectators. So here's your net ionic equation is we got 3 nickel, 2 phosphates, and then I've got making a nickel phosphate. There we go. Okay, so how about this one? Solid magnesium. So magnesium, not part of Hofbrinkel, so no subscript. And it reacts with oxygen gas. Oxygen is part of Hofbrinkel, so it's going to get a subscript here. And then it forms magnesium oxide. So when I'm writing a compound, I'm not going to think about Hofbrinkel, I'm going to think about my ion charges. And it turns out Mg is +2, O is -2, so we don't need any subscripts here. And that is a solid. Okay. So to balance it, looks like we need 2 oxygens over here, then we need 2 magnesiums. So that's our balanced chemical equation. And then to get our net ionic equation, remember what we ionize are, we ionize aqueous ionic compounds and aqueous acids. So I'm going to underline everybody who ionizes. Oh, wait, nobody ionizes. Okay, so sometimes the net ionic equation is the same thing as the molecular equation, which is what happens here. So nobody ionizes, so that means there's no spectators. So there you go. Yeah, the net ionic is the same as the molecular. That can happen sometimes. All right, so we just got one more to go down here. This one, the equation's already written out for us. This is kind of a complicated redox type reaction. And so for this one, all we need to do is figure out who ionizes. All right, so again, the ones who ionize are my aqueous ionic compounds. So I'm going to underline all the ones that are going to ionize. So this one, there we go. So these ones are all aqueous ionic compounds. So 2KMNO4, that is 2 potassium ions and 2 MnO4 minus ions. What's MnO4, if you're curious? It's permanganate. So I guess it says it over here in the name too, permanganate, MnO4. So it's one of those polyatomic ions we want to be familiar with. Okay, and they're going to react with liquid water. And then we got 3K2SO3. This is potassium sulfite. So that's 6 potassium ions. And then SO3 is, oh, it's not on this list. Okay, but SO3 actually has the same charge as sulfate. It has a -2 charge. It's on our other list. But we ended up with 3 SO3 2- ions. And actually, if you ever forget the charge of something, if you're like, oh, what's the charge of SO3? What you could do is you could look at this formula and you can say, oh, wait, I know potassium has a +1 charge. And if there's 2 potassiums for every 1 sulfite, I can determine that sulfite must have a charge of -2, because we know all these charges have to add up to 0. So you could always figure it out that way as well. Okay, and then MnO2 is a solid. So it's going to stay put. K2SO4, that's another aqueous ionic compound. So I'm going to break it down into its ions. And then KOH, so 2K plus and 2OH minus. All right. So let's look for spectators. So we've got 8 K pluses on each side. And then that's it. That's our only spectator ion. Because these ones look really similar, the SO3 and SO4, but they're actually different. So yeah, so K is our only spectator. So what's left over is you have 2 permanganate ions reacting with water and 3 sulfite ions. And it's going to make manganese oxide, which is a solid, and then 3 sulfates, and then it end up with 2 hydroxide ions. So that's our net ionic equation. That's an example of a redox reaction. If we go back and look at our reaction types, this one right here, this magnesium oxide one, that's a combination reaction. If we look over here at this table, it kind of follows this pattern where you combine two things to make one product. Combination reactions also fall in the category of redox reactions as well. So this is also a redox reaction, and we'll talk about that in a different, different video. This one up here, this is a precipitation reaction. And a precipitation reaction follows a pattern of double displacement. That follows this pattern where you've got compound plus compound, then they switch partners and make two new compounds. Okay. This one right here follows the pattern of being a single displacement, which is another example of a redox reaction. You see what this pattern is: element plus compound makes element plus compound. So here is where we see this this pattern right here, single displacement. And then last one, this is another double displacement one, but it's a double displacement, but we're forming a gas instead of a precipitate. So when you do double displacement reaction, you might end up making a precipitate, which is a solid. We tend to do the most practice with this one, but you could also form a gas. There's a few examples where a gas would form. And then acid-base reactions, we'll mainly do most of these in second semester, but that's another type of double displacement reaction. All right, thanks for watching.